What she doesn't know, or what they haven't bothered to tell her yet, and which she's dying to know, because then she'll realize that my scale is wrong, but that's okay. She'll realize that these problems that she's doing by longhand with so much trouble are really very easy. The area of the parallelogram is 5. It's the determinant of the matrix. The determinant of the matrix is 2 times 3 minus the product of the off diagonals when it's a 2 by 2 case. Bigger cases are harder to do, but we don't really need to worry about how to do much bigger matrices, because that's why we have things like MathCAD, because that's already programmed for us. Or your programmable calculator can do matrix multiplication. Right?
The cross product is linear.
Yeah, the cross product of the 2 vectors. So the determinant of that matrix is the area of that shape. The bigger the matrix, it means that you're dealing in 3 dimensions. If they are 3-dimensional vectors and you've got a collection of 3 of them, then you're figuring out the volume of a cube. If you've got a 5 by 5 matrix, you've got the volume of a hypercube, and so on and so forth. So a determinant has implicit in it the volume of a shape. And beyond that, now comes, somebody mentioned that if the determinant was 0, then there was no inverse for the matrix. Well, that makes some sense. If the determinant is 0, it means that we can't distinguish between those 2 vectors. But the 2 points are actually collinear. And if the 2 vectors are indistinguishable from one another, we can't find their reciprocal. So let's talk for a moment about since we've already brought it up. I asked you earlier what the, and I'm running out of time here. I asked you earlier what the inverse of the number 2 was. You said it was a half. In matrix algebra, it's not quite that quick. The inverse of any matrix is 1 over the determinant of the matrix. And again, the same kind of rule applies. In the 2 by 2 case, it's pretty simple. The determinant is the product of the main diagonal minus the product of the off diagonal. If you have higher dimensions, then the algebra is a little harder, but it works kind of the same way. If you want to do the inverse of a matrix, it's 1 over the determinant times the transpose of the matrix of cofactors. Now, when you took linear algebra or you did it in whatever the required statistics course was you took here as an undergraduate, they have all these really neat rules where you write down the matrix and then next to it you write a blank matrix and you have an identity matrix on the other side of the equal sign. And you take out your pencil and you draw all these weird loops and squiggles and snakes to tell you what things to multiply by in order to get the identity matrix on the right. I never could memorize that. I never could keep track of that. So I always do it the hard way. I figure out the determinant, I figure out the matrix of cofactors and take the transpose, and because one of the other things that I had trouble with as an undergraduate was accounting. Even though I was a chemistry major, I took accounting. Before I graduated, I think you got a D in accounting. I could never keep the particular numbers straight. And I had mentioned before that the inverse of a matrix is that matrix which returns the identity when we multiply the matrix by its inverse. So it doesn't make any difference if we multiply C times C inverse or C inverse times C. We still get this identity matrix, which has 1s on the main diagonal and 0s elsewhere. Independence and other things. One of the things that, I don't think we have an application this semester, but one of the things that comes up you guys have to take a time, the people in the financial engineering program have to take a time series course with, I don't know, Professor Way, maybe? Is he still teaching it next semester? Cholesky decompositions are going to come up next semester, because next semester you're going to talk about vector order regressions and structural vector order regressions, and you're also going to talk about causation. Causation in the statistical sense. Causation in the sense of temporal precedence. Not causation in the sense that Skippy caused me to eat those Oreos before dinner and spoil my appetite. Not causation in that sense. Causation in the sense that at 5 o'clock I ate the Oreos, and at 6 o'clock I sat down at the dinner table. Eating the Oreos preceded sitting down at the dinner table. So causation in a statistical sense is only assigning temporal precedence to the sequence in which things happen. And it turns out that in these vector order regression models, the order in which you write down the equations of the model matters. And one of the ways that we show why and how it matters is using Cholesky decompositions. So the Cholesky decomposition becomes important because in our structural model, the coefficients in the structural model, we can rewrite the structural model so that we cause some of the coefficients to be 0. We can operate on the model. The model might be y is equal to a times x plus some disturbance term, where y is a vector of random variables, say n-dimensional, and we have t observations on each of the n variables, so that x has to have n independent, has to be conformable to y. And in its original structure, it looks as though all the elements of y act on the set of y's. But we can transform the model. We can multiply from the left by suitably chosen matrices, such that when we're all done, we get something that might be written as z times bx plus mu. So we multiply from the left by something to create a new random vector, a new set of coefficients and the original x's, where the b gets a 0, which tells us that we're killing off one of the x's in the first equation. Okay, so the Cholesky decomposition is important. It's a way to triangularize a matrix. So all the entries above the main diagonal go to 0. Or we could do it the other way around. We could cause all the entries below the main diagonal to be 0. And the fact that we can do that is what shows us that the order in which we write down the equations of a model actually matters. You get a different story depending on the way in which you write things down. Which is another reason why you did the exercise that you did for last week. And you can change the story by altering things just a little bit. It's now 8:05, and I think we only go till 8, right? I think in one of the emails I sent you, I said we went from 5 to 8:30 in my dreams. So I'll see you next week. By next week, I will have come up with your next homework assignment. We'll be talking about linear algebra next week some more. We'll finish it off. It looks like there's a lot of stuff here to go through quickly. Oh yeah, if you decided you wanted to rewrite anything in your first assignment, first submission, give it to me now. Make sure that your pages are stapled to one another. So when I step off the curb and fall down on my way out to the car and all the pages are your pages are stapled.